now?
Да, все хорошо, спасибо.
Okay, thank you. So the last time we considered an algebraic and a fine algebraic variety X, so that the algebra of functions A is a commutative finitely generated algebra. And there is a finite group gamma acting on X, or equivalently gamma acts on the algebra of functions. And then we proved the following things. First, that the algebra of invariant functions is also finitely generated. And so we define the categorical quotient X modulo gamma just at the spectrum of this algebra of invariant. And then the second property is that A is a finite AG, A gamma, sorry. Apologize. A gamma module. And third, in case when our group gamma is finite, then X, the categorical quotient by gamma, is the real quotient like this, meaning that the fibers of the natural morphism pi x to x over gamma corresponding to the embedding of invariant algebra A gamma into A. So these fibers are exactly the gamma orbits in X. Okay. So this is the content of the last time. And today we will only consider the case when X is a vector space V, finite dimensional.
Извините, а можно
Yes.
спросить, что мы подразумеваем под X
Yes.
фактор гамма, но только не с двумя черточками, это понятно, а с одной?
What is the meaning of X slash gamma as opposed to double slash? That's the question?
Да, yes, only one slash.
Just the set theoretical quotient, so the set of gamma orbits. And this third claim means just this. Since the fibers of this algebraic morphism pi are exactly gamma orbits, this means that this categorical quotient x double slash gamma coincides with the set, just the set of points is the set theoretic quotient x modulo gamma.
But we take only closed points, yes?
Oh yes, we only consider closed points, so I avoid as much algebraic geometry as possible.
Okay.
Okay.
Thank you.
Welcome. Vanya, do you have any question by any chance? No?
No.
Yes. Okay. I saw that your mic was on. Okay. So today we specialize to the linear case, and then we consider two more special questions, namely when the quotient x modulo gamma, same the categorical quotient, is also a vector space. Okay, say let's call it 1 prime and 2 prime when the algebra of functions, say A, that is functions on V, and that's just symmetric algebra of V star, and let us call it S. We know that it's a finite model over the algebra of invariants, but the question is when it is a free module. Over the invariance of gamma that I will denote by R today. Okay, so it turns out that these two questions are equivalent, and these strong properties hold if and only if gamma in V is a so-called complex reflection group that I presently define. So it means gamma is generated by complex reflections S, and S is a complex reflection. So as you may guess, there's some generalization of the usual notion of reflection. If S is of finite order, and also the rank of S minus identity is 1. Okay, so in some basis, in an appropriate basis, S looks like some root of unity, say zeta, then 1, 1, 1. Like that. If this root of unity is -1, then this is the usual reflection. Otherwise, there is some generalized notion of complex reflection. Okay, and say so. First of all, this is a theorem. So 1 prime is equivalent to 2 prime equivalent to 3 prime is a theorem of Chevalier. Claude Chevalier. And it was proved in 1955, right after Shepard and Todd classified all the complex reflection groups. Okay. Note that the property of being a complex reflection group is not just a property of gamma, but also of its representation in V. right? Mm, and somehow the classification is a list of all possible gammas that allow a complex reflection representation V. Okay, and the classification was a certain three-dimensional series, A, P, N, plus 34 exceptional groups. Okay, so for example, all the while groups are just reflection groups. And more generally, all the Coxeter groups, finite Coxeter groups. So for example, symmetries of icosahedra. It is called H3. There's also H4 in four-dimensional space. Okay, and certainly somehow I mean irreducible groups, right? Because if you have two groups, you may take their product and it will be another complex reflection group. So when I say 34, I mean irreducible. Okay. And just to give most basic example, this is just the symmetry group, Sn, and this is G 1, 1. And its representation is just the n-dimensional representation. Oops, sorry.
Извините, пожалуйста, а можете
Yes.
еще раз, что такое J от A по N?
I didn't give a definition. I will give it in the home assignment, and also I will say it in a few minutes. I will give it momentarily. But the symmetric group just permutes the coordinates, and certainly it is generated by the usual reflections. Si, or Si of x I is x I plus 1. Si of x I plus 1 is xi, and si of xj is xj, when j is neither I nor I plus 1. Okay. These are so-called simple reflections. So this is a basic example. And by the way, let us test this Chevalier theorem in this example. So the invariant functions are polynomials in the basic symmetric polynomials, the fundamental symmetric polynomials. Well, maybe I should say E1 and so on, En. Okay, so in other words, V over Sn is another n-dimensional vector space. So it's a free polynomial algebra. And then also, this was 1 prime. And property 2 prime is that C of V has a basis x1 to the power a1, x2 to the power a2, and so on, x n maybe -1 to the power a and -1, where ai is between 0 and I -1, I think, or just one moment, sorry, so that I get n factorial. Here I will get, no, just I, just like this. Okay. Over the invariant functions. Okay. So everything works for the symmetric group, and this is a very well-known example. And now, if I consider this Shepard-Todd group G A1 N, then this is the wreath product. So it's the symmetric group Sn, wreath product with the group mu A. By definition, this is the semi-direct product of symmetric group with the roots of unity to the power n. Okay, and mu A is the group of cyclic group of roots of unity of order A. Okay, so the order, in particular, the order of this group is n factorial times e to the power n. Okay, and finally, note that there is a homomorphism, the product homomorphism. A pi from this G A1 n to the group of roots of unity. Yeah, you have n various roots of unity, and you just multiply them. You get such a homomorphism. It's Sn invariant, so there is such a homomorphism. And now we would take sort of its kernel, namely, we take inside mu A, we take the roots of unity of order A over P.
I'm sorry, how
yes.
this homomorphism looks exactly?
This homomorphism looks as follows. You have a transposition, so sorry, just at any permutation, say sigma, and then you have some zeta 1, so on, zeta n roots of unity. And it goes to the product, zeta 1 times so on times zeta n. So for a divisor P of A, there is such a subgroup of roots of unity, and we take the preimage. Okay. So this is the definition, and in your home assignment, you will find its complex reflection representation and its invariance and all this.
I'm sorry, but so you said previously that all Coxeter groups are examples of reflection groups, but we have 3 infinite series of Coxeter groups, right? AN, BN, and CN.
Absolutely. So maybe even the while groups, yeah, and they just fall into this classification, and there's also in your home assignment. Okay, so you will do this all tonight. Fine. So we will not study the Shepard-Todd classification, or you may look it up yourself in Wikipedia, for example. We will prove this Chevalier theory. Okay, so we will prove it like this. So first we will deduce that if gamma is generated by complex. Yes.
А почему там только простые нужно брать?
No, I don't claim that P is prime. Maybe it's misleading notation, but it's due not to me, but to Shepard and Todd. So all reclamations go to their hairs. So P is not prime, not necessarily prime. Okay, so it's any divisor of A, not necessarily a prime divisor. So if gamma is generated by complex reflections, then S functions on V is a free R module, where R is the algebra of invariant. It will be step 1, or maybe step A, I don't know. A. Then the next step will be that if S is a free R module, then R is isomorphic to some polynomial algebra. And finally, if R is isomorphic to some polynomial algebra, then gamma is generated by complex reflections. Okay, so this is our plan, and let us start. Let us start with the following notion. So if S is a complex reflection, then the H sub S is the invariant hyperplane. In V. Okay, so there S acts just by identity, and say LS in V star is a linear functional that has a kernel HS. And it is a proper linear functional, namely SLS is some epsilon S times LS. Okay, and now for any F in this polynomial algebra, we can consider SF minus F, and then it will vanish on this hyperplane, and hence it will be divisible by its equation, by LS. Okay, so it is another polynomial, and it is denoted delta S of F. Okay, so somehow it is a method to lower the degrees of polynomials, and we will use this method in a few moments. We will need the following sort of Leibniz formula: delta S of the product is F times delta S of G plus delta S F times G plus LS times delta S of F times delta S of G. Okay, so we'll use this. So now we're proving this part A. So if gamma is a complex reflection group, then S is a free finitely generated R module. Okay, so we start with lemma. In this lemma, we don't care about the actual nature of R, and we just say that R is a graded subalgebra of S, and it has an augmentation ideal of all elements of positive degree, and it generates the ideal I in the ambient algebra S. So let A be a basis, a set of elements in S such that their images in the quotient by ideal form a basis. Just over complex numbers. Then those elements generate S over R. Okay, the proof is just, suppose they don't and arrive at contradiction. So we consider submodule. The M is R of these EAs, submodule in S. So we want to prove that M equals R, and just we'll show this in all the homogeneous degrees. By induction. Degree. So when D equals 0, this is clear. But there is
M
nothing.
равно R. Там не должно быть M равно S.
Oh, sorry. Yes. Thank you very much. Yeah. You are right. So it is clear for D equals 0, and otherwise, let's consider some homogeneous element of degree D, and just decompose it. So this sum of our basic elements plus something else. But this something else lies in the ideal, so it can be written down as such products. So here CA is just some complex number, and RB are elements in R plus, and FB are some elements in S, but their degrees, the degrees of RB are positive, so the degree of FB is less than D. So now by induction assumption, FB already lies in M, and hence the whole thing F also lies in M. Okay, so this lemma is proved, and this is nothing, not a big deal. But the next lemma 2 already uses the complex reflection specifics. So assume that we have some elements xi in R, so in invariant, and also some elements yi in S. And I runs from 1 to some M, and they are homogeneous elements. Such that their linear combination is 0. And then a very strange conclusion. If x1 is not expressible through the other axis, then y1 lies in this ideal that was generated by the augmentation ideal of R. Okay, a very strange artificial lemma. And the proof is also
Лежит или не лежит?
it does lie.
Does lie.
Sorry, if x1 does not lie is not expressible via other axes, then y1 lies in the ideal. Yeah, thank you. So the proof uses this lowering operator. So alpha is the Reynolds projector from S to R. And we can use induction in the degree of y1. So if d equals 0, then there is nothing to prove, since it means that there are some elements z1, so on. I mean, sorry, z2 and so on, zm in S, such that x1 is expressible via the others. Sorry, zm xm. But then x1 is but by this linearity of Reynolds projector, there's alpha z2 x2 plus so on, plus alpha zm xm. Okay, so well, so it does not happen. It cannot happen if the degree d is 0. Okay, and now suppose d is bigger than 0. And S is a complex reflection. Then we apply this formula at the top of the previous page. You see this sort of Leibniz rule, but we use that x's are invariant, so we get that x1 delta s of y1 plus so on plus xm delta m of ym is 0. And now we have managed to lower the degrees of y's, in particular y1. Okay, so by the induction assumption, delta s y1 lies in the ideal. So it means that f y1 minus y1 lies in the ideal, and this is for any s, right? But now our group gamma is generated by complex reflections, so it means that say g y1 minus y1 lies in the ideal for any g, and to the product. So it's any g in gamma. Now this implies that y1 minus the Reynolds projector y1 lies in I, and finally it means that y1 lies in I. Okay, so it's a very artificial statement with a strange proof, and now we will use this statement. So try to remember it for the next page. The last lemma. So suppose that y1 and so on, ym be homogeneous elements. Such that the taken modular ideal I, they are linearly independent in the quotient. Okay, then all these elements y1 and so on ym are linearly independent over R. Okay. So otherwise, we have a linear dependency relation, x1, y1 plus so on plus xm, ym is 0. And hence, by the previous artificial lemma 2, x1 is z2 x2 plus so on plus zm xm for some zi in R. And now we just plug in the second relation into the first one. So we see that x2 times y2 plus z2 y1 plus so on plus xm times ym plus zm y1 is 0, and induction in the length of this combination shows that everything is 0. Okay, so now we are able to prove this first step. Namely, group gamma is complex reflection group implies that S is a free R module. So we already proved that choosing a system of generators of S modulo I, we obtain the linearly independent generators of S over R. So the only thing that remains is to prove that this dimension is finite. Okay, but in fact, a basis of S over R is simultaneously a basis of their fraction field. This is finite dimensional. Over R is just the order, the group gamma by Galois theory. Okay. And maybe something here needs to be said in more detail, and this will be in your home assignment. Okay? So you will do this tonight. Okay, so this was the first step. If we have a complex reflection group, then the symmetric algebra of the initial vector space is free over the invariant algebra. Now, the second step, B, that S is free over R, implies that R is a polynomial algebra. Okay. And this is also a very strange argument. Namely, we will show the following, that this claim is equivalent to the claim that the spectrum of R is smooth. And this claim is equivalent to the fact that R has a finite homological dimension and more precisely, when you consider the trivial augmentation model over R, so it's an R module. Then we can take the tensor product like this, and the derived tensor product. So it leaves infinitely many degrees. So in other words, Tor I of C C over R is 0 for big enough I. Okay, so this last property is a theorem of Jean-Pierre Serre, and we will not prove it. We will only use it. Now, this first equivalence that are, well, maybe let me say one more word about Serre theorem. So the Serre theorem says that if R is smooth, then the Tor product of any simple one-dimensional module over R with itself, so the quotient over any maximal ideal, lives in degrees up to dimension of R. Okay, and there are no more higher Tors. First, but if R is not smooth at some point, then this Tor product lives in infinitely many degrees. Okay, so as long as R is singular at some point, then at this point has infinite third dimension over R. And now our R is a graded algebra. So the spec R is a cone. And if spec R is singular, then it is definitely singular at its vertex. Okay. So in fact, this cone is not necessarily homogeneous cone. I mean, the degrees of generators of R are not necessarily all equal. So for example, the spec R could look like something like this, like cusp, yeah, if degree of x1 is 2 and degree of x2 is 3, something like this. Okay, but anyway, it's so to say quasi-homogeneous. So it's a quasi-homogeneous cone. And where does it lie? It's a cone in the Zariski tangent space at its vertex. Okay, and now it is smooth at the vertex if and only if the dimension of the Zariski tangent space at the vertex is equal to the dimension of this cone itself. But then it means that this cone coincides with the Zariski tangent space. But then it means that this is just a vector space. So R is indeed a polynomial algebra. Okay.
У меня такой вопрос.
Yes.
Вы упоминали про степени образующих,
Yes.
но, казалось бы, они не имеют значения, когда мы рассматриваем конструкцию спек. Казалось бы, степени образующих имеют значение только для прош.
Absolutely, yes. But I want to have some action of the multiplicative group, right? Because I say that this R is a quasi-homogeneous cone. What does it mean? It means that there is some action contracting it to the vertex. And to this end, I need to know that the generators are homogeneous, right? I need some grading. The action of multiplicative group is equivalent to grading. And the grading comes from degrees of generators. Okay? Okay, so we proved these equivalences, but we didn't prove the part B yet, right? We still have to check something here. Namely, we will check this finite homological dimension. Okay, and this is a very simple trick. So we have to compute the derived tensor product. of augmentation model with itself, and we rewrite it in the following way. It is the product of C over R with S product over S with C. Okay. At this point, nothing happened, but now we rewrite it using associativity of tensor product. So we no, so sorry, I don't mean this. I write it as C tensor R over S, or maybe let me not write this. Tensor over S with C, and let me denote this by M. And what do I know? That M is
А вы не забыли здесь,
concentrated. Pardon me?
извините, вы не забыли здесь производную?
Okay, let me write the derived factors everywhere, but then I know that M is concentrated in just one homological degree.
Здесь обычный функтор, потому что других размеров.
Right, absolutely. Since
I'm sorry, what's the derived tensor product?
It is some general homological algebra construction. So I replace the models in question by their free or projective resolutions, and then tensor those, and it will not depend on a choice of projective resolution up to homotopy. So it is somehow well defined. Okay, but we know that S is a free R module. So this M will be concentrated in just one homological degree. Okay, and now we have to take M tensor C over S derived has a finite homological amplitude, since S it was just polynomial algebra, was smooth. Okay, it doesn't even you don't need some abstract theorems. Just use Kashula resolution. It has length n, and there we are. Okay, so all in all, this augmentation module C over R has finite homological dimension, and if R was not smooth, then it would necessarily have infinite homological dimension. So B is proved. A very strange proof. Okay, so it remains to prove C, namely that if R is a polynomial algebra, then gamma is generated by complex reflections. Okay, and again, this is a very tricky, simple proof, but looks somewhat artificial. So we consider a subgroup or the subgroup gamma not in gamma generated by complex reflections. So we want to prove that it coincides with gamma. But we don't know this yet. So we consider some intermediate invariant ring. So R prime, this is the invariance of gamma naught. So we have R, and here R prime, and here S. And now the point is that our all the complex reflections in gamma lie inside gamma naught. So there are no in particular, there are no complex reflections outside of gamma naught. Okay, and the complex reflections are those that have invariant hyperplanes, invariant divisors. So no element in gamma minus gamma naught has a fixed hypersurface. For a hypersurface divisor, and it means that the ramification indices of any divisor in the spectrum of S over the spectrum of R and over the spectrum of R prime are the same. Same. In other words, the spectrum R prime is non-ramified over the spectrum of R. And maybe if you had some course in basic number theory, you know that this ramification is controlled by the discriminant. Yeah, so in general, the spectrum of R prime is ramified over the zero locus of the discriminant ideal or divisor in the spectrum of R. And now let us compute it. So we know in this case, since there is no ramification, the discriminant must have no zero, so it must be a constant. So no ramification implies this discriminant is just a constant. On the other hand, we can choose a homogeneous basis, say Q1 and so on, Qn, or maybe Qk, of R prime over R, right? We know that R prime is free over R already, right? Because our gamma naught is generated by complex reflections, so by step A. Know this, and then the discriminant is the determinant of the trace pairing matrix. Of I Q J. And somehow, just to know where we're standing, say, Misha Goldsblatt, can you tell me if you know this? The discriminant is the determinant of the Gram matrix. Or maybe Misha Goldsblatt, yes.
Well, I think I do not know it.
You do? I don't hear.
I do not know it.
You do not know. Okay. And say, Lisa Nesterova, do you know this fact?
Yes.
You do. Okay. So then you can say look it up in whatever Van der Waarden algebra book or Lang algebra book or whatever, any basic textbook on algebra. Okay. Now, what do we know? That
Сейчас, Миша, ты говоришь, что
yes.
штрих свободен над R?
Oh yes. Oh yes.
Почему?
Right, because somehow this Galois group is gamma naught, right?
Сейчас, разве это?
Isn't it?
R' это инвариант гамма 0 вес.
Yeah, maybe that. Right. The R prime is invariance of gamma naught, and yeah, indeed. Why is R prime free over R? Sorry. Then maybe we have to use our previous argument in part B, right? When we know that R is smooth, yes, so then yeah, no, so what we've claimed here, that yeah, that this is equivalent to being free module, right? So here you see the polynomial property of R is equivalent to S being a free module over R, right? And now now R prime is also polynomial, right? Dima. R prime is also polynomial because it's invariance of complex reflection of smaller complex reflection group, right? So we have one polynomial algebra over another polynomial algebra. It's necessarily a free module. Okay. By step A n plus B. Okay. So once again, this discriminant is a principal divisor generated by this element that is determinant of the trace pairing matrix. And if degree of Qi, yes.
I have a
Yeah.
question, but it is a question about like 20 minutes ago. Here we had claimed that ладно, давайте по-русски. В общем, здесь есть производные функторы, мы говорим, что на самом деле, ну, что там только в одной компоненте получается, и поэтому это обычный функтор тензорного произведения. А я правильно понимаю, что мы здесь используем эту...
No, we don't claim this. We well, let me finish here, and I will return back there. Okay, I will finish here just in a moment. Let small q be the degree of the capital Q generator, and then certainly the degree of trace of Qi Qj will be equal to the degree of this Qi Qj, so it will be Qi plus Qj, and hence the degree of the whole determinant will be just 2 times the sum of all Qi's. And on the other hand, we argued before that this discriminant was just a constant. So it must be 0, hence all the Qi's are 0 identically, hence Qi's are just constants.
How do you infer that the degree of discriminant is this large? Why don't they just cancel out?
Because they are positive. Yeah, all our algebras are positively graded. Right? All the degrees are positive.
I mean, in the determinant, you have like n factorial summands, so they can just all cancel out.
But if they cancel out, then you will have just 0, right? Because so we have homogeneous elements of degree of this degree, twice sum of Qi. In principle, they can cancel out, but then they produce an element 0, no, not a constant. Well, a constant, but 0 constant. Okay, and this certainly does not happen. The discriminant cannot be a totally 0. You cannot have morphism ramified everywhere. Okay, so it means that R prime is just R, and hence gamma naught is gamma by Galois theory. Okay, so we have proved this, and now let's return where Elizaveta asks. Oops, somewhere here, yeah.
Yes.
Yes. So what was your question?
One moment. So, сейчас, вот, когда мы говорим, что мы можем снять производное тензорное произведение, мы на самом деле здесь как раз и пользуемся теоремой Сера, про то, что
No, but we never remove any left derived here. Only I claim that, well, first of all, if you tensor S with S over C, then there is no derived, right? Because S is a free S module.
Да,
this middle term. Now, in the right term, there are two derived products, but in fact, the leftmost one is not derived either, because S is a free R module, right? So this M lies in degree 0. But then it is not free S module anymore, and the rightmost C is not free module either. So here we will obtain some derivedness, and it will go n steps to the left. Okay.
Хорошо.
But somehow we translated all our problems to S, and S is a well-behaved polynomial algebra. But we didn't know this about R in advance, so we managed to transfer the problems to S.
Okay, спасибо.
Welcome. If there are some more questions, you are welcome.
So why the discriminant of R prime over R cannot be 0?
The discriminant cannot be 0 identically, because this morphism is somewhere non-ramified. The discriminant is non-zero ideal. It is always a non-zero ideal. It can be a trivial ideal, one, the whole ring. Yeah, if you have nowhere ramified morphism, but it cannot be totally 0. Well, somehow just generically, right? If you go to the fraction fields, then you know that the discriminant is some non-zero element. In other words, the trace pairing is non-degenerate.
So it is true because we are in characteristic 0.
It can be degenerate if you are in characteristic P and you have inseparable extension. But where in characteristic 0, the extension is separable and the trace pairing is non-degenerate. So Misha, what did you want to say?
Oh, okay, I see. Because we are in characteristic 0, so all extensions are separable.
Yes. Okay, and any more questions? If not, let me save the lecture notes, and I will send them to you momentarily, and I will see you on Thursday.
Простите.
Yes.
Вопрос уже не по делу, а скорее просто задачи прислать.
Pardon me? Say it again, please.
А можете мне, пожалуйста, задачи выслать, потому что, как я поняла...
Oh, yes, I will do this right away. Yes. I will send the exercises to everybody. Thank you.
То есть еще всем не прислали.
Okay, so bye-bye.
Thank you, bye.
Thank you.
Thank you.